Well, 2D or two-dimensional signal processing takes place in discrete space. That is, the space variable is a discrete valued quantity rather than being a continuous valued quantity. So we have a two-dimensional array of numbers or pixels, each which has a value, illustrated here in this picture, which has been represented on a very coarse grid of pixels. So you can see that each point in the image is defined by a unique color. And this then is something that we can store in the computer and consequently process with the computer. So in the discrete space case, we're going to index our pixels according to rows, the m variable, and columns with the n variable. We'll describe the value at a particular pixel m, n as the function f. So this is defined over the surface m, n. We can define a system that operates on this image, f of m, n, and if we make it a linear shift-invariant system, just like we described in the continuous space case, linear means that if I apply it to a sum of images, I get a sum of outputs, and shift-invariant means that the characteristics of the processing are independent of what part of the image we're in. I can write the output as a convolution of the impulse response of the image with the input f of m, n. Here we've defined h, the impulse response, is the output of the system when you put an impulse in. This is also the point spread function because it declares how a point for an input spreads throughout space. We can write out the convolution in some form over the two-dimensional space as h convolved with f is the sum k equals minus infinity infinity, L equals minus infinity infinity, h of m minus k, comma, n minus L, f of k, comma, L. So it has the same form as one-dimensional convolution with the exception of now that we're doing these operations over two variables and we're getting two output variables. So k and L are the variables that we're summing over, and m and n are our output variables. Well, if we consider the case where our input image f is 0 outside of some interval, here we're letting it be non-zero on the interval 0, little n equals 0, to little n equals capital N minus 1. So we've got a total of n values, and we're also going to let it be 0 on that same interval for m. In that case, my index of summation, rather than going from minus infinity to infinity, it simply reduces to 0 to capital N minus 1. So they're the only values of f that are non-zero. So we can think about a graphical procedure for doing this kind of convolution that parallels the graphical procedure we use for one-dimensional convolution. We're going to take h, our impulse response, we've got h of k, comma, L, and we want to get h of minus k, comma, minus L. And that's obtained by flipping h horizontally and vertically. Okay, that's a reflection in both of the coordinates. Then we're going to shift this flipped version to the location m, comma, n. And what that means is that h of 0, comma, 0 is located at indices m, comma, n. So whatever value there was at 0, comma, 0 in the original h now shows up at m, comma, n. Then we form the product by multiplying this flipped and shifted image times the original image. We form that product and then add up all the values in the product to get our convolution result. So I have a simple example here in which we have a h system that has a 2 by 2 set of pixels that we're going to use for its point spread function or its impulse response. We've got h of 0, 0, 0, 1, 1, 0, and 1, 1. And then our image f in general is an n by n image. We want to look at the convolution between h and f, and we're going to call that g. So first of all, in steps 1 and 2, we're going to flip and shift h. So if I flip h horizontally and vertically, I get this form here where h of 0, 0 is now in the lower right corner, h of 1, 1 is now in the upper left, h of 0, 1 is in the lower left, and h of 1, comma, 0 is in the upper right. That's a consequence of flipping my original matrix. I'm going to flip the rows, and then I'm going to flip the columns, and that gives me this one here. Now then, in step 2, I'm going to shift this matrix so that whatever was at 0, 0 in the original now locates at n comma m. Okay, so the location of this term in the matrix is at row m and column n. So for the third step, we're going to multiply the two images, the flipped and shifted h and then our original image f, and add up the values. So to do that, we're going to consider some specific cases. We're going to consider the case where m is equal to 0 and n is equal to 0. In other words, we're trying to compute the output at pixel 0, comma 0. Remember, we shift the h of 0, comma 0 element ends up lining up with m and n. So here's my k-axis and my l-axis, and so m is at 0 and n is at 0, so h of 0, 0 overlaps with f of 0, 0, so I multiply those two, nothing else overlaps, and therefore my output, g of 0, comma 0, is h 0, 0 times f 0, comma 0. Well then, if we go on to the g 0, comma 1 output, that's when m is 0 and n is 1. So now I've shifted my impulse response matrix H so that it lines, so the h of 0, 0 term lines up with 1, so n is 1 on the k-axis, and m is still 0. Now I have two overlapping terms, and when I multiply these two and add them up, I get that g of 0, comma 1 is h of 0, comma 1 times f 0, 0, that's these right here, plus h of 0, 0 times f of 0, 1. So that's this product here. So that's my g of 0, 1. And then if we were to continue this process, you'd see that in general, as we shift and overlap this matrix H with different parts of the image, and I form the product and add them up, what I'm going to get in general is that h of 0, comma 0 is overlapping f of m, comma n, because 0, 0 always is shifted to m, comma n, plus h of 0, comma 1 times f of m, comma n minus 1, plus h of 1, comma 0, f of m minus 1, comma n, plus h of 1, comma 1, f of m minus 1, n minus 1. So that would be my output. And what you see here by this graphical procedure is that the columns of H filter the columns of F. I have H, the columns of H are operating over the columns of F. Similarly, the rows of H end up filtering the rows of F. And that provides us with some very useful insight into how these point spread functions affect the output, what the image output might be if we use a particular filter. And you can generalize this, of course, beyond the 2x2 case for H to more complicated or larger extents. So let's consider a couple different choices for H. Here I've got one where H is 1/4, and then I've got 1, 1, 1, 1. So what's going to happen in this case is that I'm going to get the mn pixel by taking an average of the 4 pixels in the vicinity. This blurs the image then, because when I replace the pixel by the average of 4 pixels, I'm losing the resolution or the details that are present on a pixel by pixel variations. So what about case 2 here? In this case, I'm going to be, remember that the rows of H filter the rows of F, the columns of H filter the columns of F. So in this case, I'm combining columns, I'm averaging columns. In one case, the columns have an opposite sign, but it's still an average. And here I'm averaging the columns. So across the columns, I'm going to cause a blurring. And then across the rows, I'm taking a difference. So there, I'm going to accentuate high frequencies or accentuate changes in the image. So in this case, we're blurring things vertically, but we're accentuating differences horizontally. Well, this third case is very similar. It's just in a different direction, because now I'm averaging horizontally and I'm differencing vertically. Remember, the rows of H filter the rows of F. the columns of H filter across the columns of F. So when I have this difference taking place across the columns of F, I'm going to have a accentuation of differences, of transitions, and so on, whereas I'm blurring such things when I go across the rows. So in this case, we're accentuating differences vertically, we're blurring things horizontally. The last case I'm going to discuss here is when I'm taking a 3x3 filter point spread function, and in this case I'm going to form the output ends up being the average of these 9 pixels. So since I'm averaging 9 pixels, again I'm going to blur the image. And in this case, because I'm averaging more pixels than I was up here in case 1, I'm going to have a greater degree of blurring that takes place. So with a little bit of understanding of how the two-dimensional graphical convolution operates, we can gain insight into how a particular point spread function is going to affect the quality of the filtered image. We probably aren't going to want to do two-dimensional convolution very often by hand, but it's more useful for the insight that it gives us in terms of understanding the behavior of our point spread functions.